Oh, sorry. Yawn, yawn, yawn. All right. So, yesterday we finished up drawing our galvanic cells, and we were moving on to talking about cell potential, electrical work, and electric and free energy. So that's where we're at today. We're going to bring in this guy. This is a new equation that we're going to be working with today, so you should be ready for that. So get your calculators out.
We can't see your board.
Are we in? Which page of the packet are we in?
Help him out, please.
This.
Packet on page like 6 or 7.
Oh, I'm like, sorry.
All right, so we are on page 7 in the packet. There we go. All on the same page now. All right, so finish up galvanic cells, ready to talk about this. This is going to be our free energy, is going to be the stuff that we can use to do work. Okay, we can power your cell phone batteries, or cell phones. We can, you know, when you were little kids and you had the toys that would move around and dance and stuff, that's what they would use that for. It can power the light bulb on a flashlight. Okay, that's the free energy. So when you look at that, you're going to be working with some ideas. This is called electromotive force. We measure that in volts. Okay, and they give it this weird little E symbol here for electromotive force. It's going to equal work over charge. Okay, now they don't have that exactly, do they? No, they don't have that exactly on your sheet, but they do have on your sheet, the very, very last thing in the corner here is that they have 1 volt equals 1 joule over 1 coulomb. And if you look here, you can see this guy is measured in volts, right? And these are joules and coulombs. So they have this, they just have it with units instead of the word work and charge and EMF. So that's on this sheet, your formula sheet. Okay. So when Faraday got a hold of this, what he said was that the charge on 1 mole of electrons equals this many coulombs. And again, that is on this sheet. That value is right here. Okay. So the charge on 1 mole of electrons, and that's key. I've seen them ask questions about what's the charge on the electrons, but you don't have a whole mole of them there. And so you got to use your dimensional analysis to figure it out. So be very, very careful. And it even says on here, Faraday's constant equals per mole of electrons. So Q then is going to equal the number of electrons times Faraday's constant, which Q was charge, okay, in coulombs. So coulombs will equal the moles times Faraday's constant. This formula is on there. And this is why I have been having you write every day N equals this number. Because that N value is going to be the N value that you're going to use in this formula. Delta G then, delta G prime, that means that it's at standard conditions, 298, 1 molar, and 1 atmosphere. That's going to equal negative, so that we can get the charges right and everything, the values. Negative moles of electrons times Faraday's constant. Again, you don't have to memorize this number. It's on your cheat sheet that they give you. And then your E. So this is your voltage that we've been figuring out as well. Okay? So if you're given these things, you can calculate delta G. If you're given delta G and you're given these things, you can figure out F. All right. If you have a negative E, that is non-spontaneous. Positive E is spontaneous. That makes a good battery. All right. So we are going to calculate delta G here. And I need to do a little snapshot of this. So we are going to hopefully this will give me enough room to write on it. Yes, good. Okay. So we're going to go back and we're going to use these reduction potentials that we had up here in this chart. We are dealing with copper going to losing 2 electrons. So copper 2 electrons is 0.34. So Cu is 0.34 volts. And the Fe with 2 electrons as well. So this guy's already balanced for us. Isn't that nice? Here we go. Fe is going to be 2 electrons. Fe down here. Here we go. So negative 0.44. So this is a negative 0.44. So just by looking at these values, you should be able to tell which one's being reduced, which one's being oxidized, and then from that you can derive which one is your cathode and your anode. So just from these values, how can I tell which one is going to get reduced and which one's going to, without even having this up here? If I just knew copper and iron and I look these values up, how would I know which one of these is oxidized and which one of these is reduced?
Copper.
More positive.
Right, the reduced is more positive. So this is going to get reduced, this is going to get oxidized. And if you look here, iron is going to lose electrons. We can see from the equation that they gave us, but it's still good for you guys to start seeing that. You know what I mean? I want you to start being able to see that happening just from these values. I want you to be able to see different ways to figure this out. Here, my copper is gaining electrons, and here, so reduction is gain, this is oxidation. All right, now, once we figured that out, we know that whatever's reduced, is that going to be my cathode or my anode? Cathode. Remember, your consonants go together. That means that this is your anode. So oxidation, so they say an-ox and a red cat. They even oftentimes will say a fat red cat because the cathode is going to be getting bigger. This is going to be gaining copper atoms. So if we had our electrode here, it's going to get bigger and bigger and bigger as we move along. This iron, though, is going to get smaller and smaller and smaller and smaller until it's all used up and all of its electrons have been transferred. So this will get smaller. This is going to get bigger. All right. That's just a little bit of a review from the stuff that we studied yesterday. Now, I told you to figure out our delta E. Delta E, then, prime. I always tell you to take the cathode minus the anode. Okay? If you follow through the way she does it, if you follow through some of the you can, we can stuff that I gave you, they will have you reverse reactions. But I think that my way is faster and it's solid. So just remember, cathode minus anode. That's the order. So I'm going to take my cathode value. I'm going to minus my anode value. But that was a negative, right? So 0.34 minus a negative 0.44 is going to give me 87 volts. And it's a positive value. So this reaction has a positive value for this. Now, we need to check this out in terms of our delta G. They wanted us to calculate our delta G and say if this was going to run or not based on that. So my delta G then is going to equal a negative NFE. My E is right here. That's the 0.78. That's what we just calculated. My Faraday's constant, I'm going to get that. That's 96485. Sorry, 485. Okay. My N value, we still need to calculate that. We need to figure out what our N value is. So we're going to go back up here. And we can do our overall reaction if we want. So we've got our copper 2 plus. It's going to pick up 2 electrons, and it's going to form Cu. And then those 2 electrons will have come from the iron. Iron Fe would have come from that 2 electrons plus Fe 2 plus. So my N value is what here? 2. And remember, the formula travels with a negative here. So we're going to calculate our delta G equals, this ends up being a negative 150,516.6, and that's joules per mole. I guess I should have talked to you guys about units here. So I'm going to go back and do that real quick. Red. So this is 2 moles of electrons times Faraday's constant. Faraday's constant is 96485, and that is coulombs per, so C per mole of electron times our E value, which is volts. We need to talk about C in just a second. I'm going to get rid of him again in a second here, okay? But E is volts here. So our E value was 0.78, and that was going to be volts, okay? Now let's talk about what a coulomb is, okay? Volts equals joules per coulomb, right? So coulombs equals joules per volt. Yes? Everybody buy that? So I'm going to sub out this coulomb here for joules per volt. Joules per volt. So then, when I do that, my volts are going to end up canceling here. And my moles cancel. So it's going to leave me, how did I end up with joules per mole for my answer?
Isn't N something? Isn't
Oh, electrons per mole. Yeah, N is moles of electrons, moles electron. But wouldn't that mean that those would cancel?
those electrons? It's moles electrons or electrons. moles of electrons.
It says Faraday's constant is coulombs per mole electron. Oh, so this had another mole here. Coulombs per mole. That's why. So these moles will cancel, but this mole will remain. That makes sense.
Wait, a mole is also.
Well, the unit is 98485, right? And it said that is coulombs per mole electron. And this is a mole of electrons. So this is moles of electrons. Yeah. No.
So the mole that you have, the joule goes on the bottom. Because it's coulomb over.
Yeah. This is why I hate physics. Anyway, they cancel out and you end up with joules per mole. You shouldn't. All right, anyway, this ends up being a negative value. So if this is a negative value, all they asked us for was to, well, no, they said calculate the delta G. So this is our delta G here. The delta G will equal, and that would be a negative 151.2 kilojoules. I'm still stuck on those units. I'm gonna have to go back and revisit that.
You just move the mole to the bottom. There should be 2 moles on the bottom. And 1 will cancel.
Okay. So electrons per mole. And this was joules per mole. But then, oh, that's just electrons then? 2 electrons per mole. So shouldn't moles be down here? So how are we canceling moles? Wouldn't moles square then? That's why I hate physics.
It's moles of electrons, so it would just be moles on top.
So just moles on top here?
Yeah.
But then wouldn't the moles cancel?
There's a second mole because of the
Okay. Well, I'm just glad you guys understand it. Moving on.
just trust this one.
Moving on. That was painful. That's why I hate physics.
And that's why I hate dimensional analysis.
Oh, dimensional analysis. Great. Did we do this one? We just did this one, right?
Yeah, number 4.
Okay, so using this table here, all right, so we're going to predict whether this will dissolve. Okay, so if we look up the potentials for these, this ends up being a 0.96 volts, and this ends up being 1.50 volt. What?
I'm confused where we get those values.
They will give it to you on a table on the test, and you have it on a table.
Which one?
It doesn't matter. The tables are both the same. This one just seems to be a little more complete. So gold is probably found over here somewhere, I'm guessing. Yeah, here. So this is 1.5, so that's where I got that one from. And then NO3 is here, so that's a 0.96. That's where I got that one from. So in order for something to dissolve, which one's doing the dissolving, the anode or the cathode? Which one's getting dissolved? Which one's getting bigger?
The anode.
Anode, what?
Or no,
It's a fat cat.
Yeah.
The cathode's getting bigger, which means
Yeah,
the
the
anode's getting
anode
smaller,
dissolves.
right? So in order for this to dissolve, in order for our gold to dissolve that they're asking about here, that means that gold would need to be what? This needs to be oxidized, right, to dissolve. This needs to be our anode, correct?
Yeah.
Is this going to be our anode based on these values? Why?
Because it's more positive.
Right, it's more positive, so this would be our cathode, this would be our anode. So this guy is not going to dissolve. Make sense? Now, do your notes keep going here, or is this where I stopped? That's where I stopped, wasn't it? I didn't talk about the Nernst equation. Okay, all right. So that's where we stopped today. We will pick up on Nernst equation tomorrow, and he is one of our last equations of the year. Exciting times. Austin, I will bid you adieu unless you have questions, my child.
All right, sounds good. See ya.
All right, bye, hon.